Thanks so much for joining us. We're really happy to have you here and our speaker here. We are part of Austin Water's Wildland Conservation Division, which includes two programs: the Balcones Canyonlands Preserve, which protects endangered habitat in western Travis County, and Water Quality Protection Lands. The Water Quality Protection Lands safeguard groundwater in the Barton Springs segment of the Edwards Aquifer through conservation and restoration of large connected natural areas in Hays and Travis County. By protecting and restoring native grassland, savanna, and riparian areas, the WQPL not only supplies high quality water to recharge the aquifer, but it also provides habitat for many local species of plants and animals. We're happy to have Devin Grobert with us today to speak about fire, water, and biodiversity in Central Texas ecosystems. As a senior biologist of Austin Water's Water Quality Protection Lands program, Devin works to restore ecosystems in Central Texas and especially enjoys working with seeds, fire, volunteers, caves, and environmental data. Devin has a master's degree from Colorado State University in rangeland ecosystem science and is currently a PhD candidate in plant ecology at UT Austin. In his free time, he enjoys reading, cooking, spending time with family, and especially doing that in the great outdoors.
Hi, everybody. Thanks so much for being here. I'm a senior biologist with the Water Quality Protection Lands. I think Audrey mentioned I'm doing my PhD at UT, and I have a chapter on ecohydrology, mentored by Daniela Rempe on that project, brilliant hydrogeologist over there. I also have worked with Brad Wilcox, one of the co-authors of our WQPL land management plan, who's kind of one of the, really well-cited and accomplished eco-hydro type researchers in the Southern Great Plains and especially the Edwards Plateau. So that's kind of the experience base this is coming from. So in summary, first I want to characterize the landscape as kind of a dynamic ecosystem. We'll do a little bit of eco-hydrology basics. We'll talk about the response of vegetation and hydrologic function to disturbances. A few brief notes on how karst terrain kind of is a special case for ecohydrology. And then a brief conclusion: what can we do and how do we operationalize this kind of information? So Central Texas is a dynamic landscape in a way that's pretty hard to miss. Indelible changes on the land from development and high human populations. Austin and San Antonio are connected by 75 miles of continuous urbanization, including the vital region around San Marcos and a string of the fastest growing small cities in the nation. That's a little quote from this article about the Texas Triangle, the idea that this area between Houston, San Antonio, and Dallas-Fort Worth is all kind of gradually urbanizing. Another one, Texas heat wave, an exceptional event driven by climate change. Look at the date. That's what we thought, June 13th of this year. We had no idea what was coming. And then heat, drought, and population growth have stressed aquifers that supply water to millions of Texans. I think if you were like a supervillain and you really wanted to dry up the aquifer, you would turn up the heat, you would make droughts longer, and you would pull as much water out of the aquifer as you possibly could. And that's what we're doing. I'm not saying that there is a supervillain behind these things, but there are signs. So it's a dynamic landscape in ways that are really obvious, really recent, really indelible. But I kind of think it's also a dynamic landscape in some intrinsic ways, some longer term ways. One of the ways we can understand the inherent properties of an ecosystem is to look at historical ecology. Here's an account from John Bartlett. This is when he's traveling from San Antonio to Fredericksburg in 1854. He says, open grassy plains occur at intervals, with clumps of live oak giving a cheerful and picturesque appearance to the landscape. Bits of rolling prairie covered with luxuriant grass, with here and there a clump of live oaks, continued as before. Limestone frequently appears above the surface. And here's where he's almost arrived in Fredericksburg. The country, since we left San Antonio, consists of low hills with broad intervening valleys and is covered with rich mesquite grass. Clusters of live oak abound in the valleys, while the hills are comparatively bare of trees. So it sounds like kind of a prairie ecosystem, grass-dominated kind of system. But wait, here we have Olmsted, famous landscape architect in Texas in 1857. He says, at noon, we forded the Blanco, the principal branch of the San Marcos Range. Beyond it, our road approached closely the hill range, which is made up of spurs coming down the mountains north. They are well wooded with cedar and live oak. And Ferdinand Lindheimer, sometimes called the father of Texas botany, also kind of one of the prominent field naturalists of his day in the world. He says near New Braunfels, it grows on the hills on the plateau, which is here 200 feet high, full of ravines that are densely covered with cedars and underbrush. So these different observations probably came from areas that were really close to each other and kind of right where the WQPL is today located. And yet there seems to be this kind of tension between these descriptions. Some suggest more grass dominance, some suggest more woody dominance. So to kind of reconcile this tension, we can look at another data stream or other data streams. So there's hard physical evidence. The image on the upper left is fossilized pollen from from Friesenhahn Cave. That's in Bexar County near San Antonio. The panel on the left shows change over time in the cover of C4 grasses in the deep riparian sediments, which kind of a rare kind of data set from this region, on Fort Hood, so a little bit north of here. And then the one in the middle, kind of middle left, is from Freeman Ranch. And basically the first two, Friesenhahn Cave and this Cow Creek, Fort Hood riparian sediment deposition, just show fluctuating cover by woody plants and grasses over time. The one in the middle is a much shorter data set, only a few hundred years or something. And it just shows recent woody encroachment into grasslands. It's consistent with that signal anyway. This signal is consistent with that narrative anyway. But it also shows that in the center of these woody clusters, they were wooded for a really long time. And then the panel on the right, these plots on the right show from Hall's Cave. So drier, more central Edwards Plateau, 800 millimeters of year compared to our millimeters of rain per year compared to our 930 or so. Shows, you know, this same signal, fluctuating dominance by woody and herbaceous cover over time. So all of these kind of make sense if you put them together. The settler accounts, these different places in the Edwards Plateau with kind of fluctuating woody and herbaceous cover over time show this picture of a shifting mosaic kind of savanna system where we have long ecological antiquity of both woody cover and herbaceous cover. And so they both have really important consequences and urgent sort of missions and mandates to inform conservation work. Also, they have pretty different consequences for hydrologic function. So that's kind of what we're going to talk about for the rest of this talk. This isn't like super on point, but I just want to point out the red boxes on this image on the right from Hall's Cave cover the part of the history from this site. This is phytolith data, fossilized plant pollen data. And the red box shows when there was more consistent human occupation. So further back in time, there were significant periods without humans or intermittent human presence in the watershed. But the red box shows a lot more chipped rock, arrowheads, hand axes, things like that. We also see the bottom panel on the right in that gray box, a lot more charcoal in the system. The green box shows more consistent grass cover, and the navy blue box at the top shows higher and more consistent oak cover during this period with consistent human occupation. We see that kind of signal throughout the central part of North America. Anytime there's more people on the landscape, there seems to be more fire, more grass, and more oak trees. If you want to learn more about why Native Americans would have cared so much about grass, I'd recommend the recent PBS documentary on bison from Ken Burns.
One more point I want to clarify about this slide is that, you know, when we talk about a shifting mosaic land cover in the Edwards Plateau, we're generally talking about decades to centuries type time scale. So we have some abiotic site types that are probably more conducive to grassland dominance, and other abiotic site types that are more conducive to woody plant cover, and then this large in-between area where it fluctuates over time. And a key moderator of vegetation cover is probably disturbance, mainly from fire, from herbivory, or from drought. But when we're looking at paleoecological data, this is like millennial timescales. So that's a different kind of source of information. So throughout North America, most everywhere has changed. You know, the vegetation cover has changed oftentimes in multiple directions over time, and not all of those sites are like shifting mosaic type savannas. So that's not exactly the point I want to raise with this kind of data. More, I think this tells us that we probably have had savannas for as far back as we can tell in the Edwards Plateau. So some things that substantiate that idea are the prevalence of genera associated with full sun in the Asteraceae, the Poaceae, Ephedra, Opuntia, as well as, of course, the juniper and oak and other woody plant genera. And then another reason I think this kind of information is useful is because climate change is predicted to give us changes that we haven't seen in the decade or century timescale. So looking at deeper ecological antiquity could be also helpful in predicting and interpreting what kind of changes we should expect to see with anthropogenic climate change. So I mentioned one of those disturbance types that probably impacts vegetation covering the Edwards Plateau in a big way over long timescales is fire. And I think another way to learn about the intrinsic properties of an ecosystem is to just look at the basic biology of the dominant species. So we know we have a climate that's capable of supporting closed canopy woodlands, and yet a vast majority of our native flora in the Edwards Plateau and the hill country is full sun adapted. And so one of the key processes that is associated with that pattern around the world is fire. And the way that we see that is a regular recurrence of fire, or perhaps some form of recurrence of fire. In other words, you can't just have one fire and expect that to have these, maintain your grassland for centuries or longer, and in fact impact the properties of the native flora. It takes kind of a fire return interval. And I think that's important. We'll talk about later in this presentation, the idea that we have the hydrologic response to changes in woody plant cover are only effective for a pretty limited time scale, right? So one of the meta-analyses we'll talk about later shows something like 2.5 to 8.5 years after changes in woody plant cover do we expect for hydrologic response to remain statistically significant. So if we want to do land management to impact water cycling, we need to have a fire return interval. And in fact, that's consistent with this kind of savanna ecology and savanna land management regime that requires a fire return interval. In our case, I think, most people think it was something like 3 to 7 years. The more formal studies, I think, point more to like 2 to 5 years for fire return interval. I expect that in sites with intermediate land cover, woody plant cover, you probably need to do a pretty tight fire return interval for like a restorative regime. But if you already have low woody plant cover and you just want to maintain that, you can probably do a much longer, a decade, perhaps even longer, fire return interval. So here, this picture on the right is a no-lina just a few days after burning, and it's having this outrageous floral response, right? You wouldn't expect to see even 1% as many blooms if that plant had not been burned a few days prior. So that's like an example of like a biological adaptation that's specialized and for fire. Here's a list of the endemic species from the Eastern Edwards Plateau relative to 3 categories of shading. This was provided by Bill Carr in support of the WQPL land management plan that was formally adopted by council, or approved by council earlier this year. And they show, of these 3 categories of shade tolerance, full shade, partial shade, or no shade, for species that are endemic to the Eastern Edwards Plateau, the category with the most species in it is no shade. So, that's one sort of data stream to interpret what kind of system we're dealing with. So, and then we've got a bunch of species that are adapted to partial shade or no shade. And then the smallest category is adapted to full shade or partial shade. But note that, that is still starting on this list with the anemone, edwardsiana, all the way down, all the rest of the species. That's still a lot of species that are adapted to full or partial shade. So we see in this stream of evidence that we have a deep ecological antiquity of both full sun plants, but also full to partial shade plants. So again, kind of another way of getting at this message that both grassland and woodland ecosystems have these historical legitimacy and urgent conservation missions associated with them.
We're shifting over to ecohydrology now, the main topic of this talk. So most, maybe all ecohydrologic research relates in some way to this water budget equation. So here I've got the basic form. Precipitation is kind of all of the water flux in the system. That's like the total water budget comes from precipitation. On the other side of the equation, we have that precipitation is equal to evaporation plus transpiration plus runoff plus recharge. If you can measure all of those things put together, you can have a closed water budget equation. That's kind of like the aspiration of all ecohydro research. And it's rarely perfect, right? It's rarely met. And there's endless ways to kind of split out these different things. For example, precip, you could look at just growing season precip, just cool season precip. You could divide out evaporation into evaporation from the surfaces of plants, from the litter layer, from soil moisture. You could break out transpiration from grasses and from trees. Transpiration is, of course, water lost from leaf surfaces in support of plant metabolism. So you could compare transpiration, you could measure it from different species of trees, for example, and you get this scientific research that just kind of gradually becomes more granular, more refined, more detailed, more complicated understanding of the system. Recharge is another one that's been broken out a lot into diffuse recharge, which is water that kind of percolates through the epikarst, a term we'll define a little later. That's kind of like, between the soil surface and the top of the aquifer. So I guess we're defining it right now. And so that's diffuse recharge, and discrete recharge is kind of rapid flow of water directly into voids, conduits, and caves into the aquifer. So ecohydrology research generally tends to relate to this basic equation. We use this mathematical equation to drive more refined, precise, and rigorous research. So one of the kind of key findings in this field, in the 70s, people were reporting changes in water yield associated with changes in woody plant cover. So Bosch and Hewlett compiled a bunch of these studies in the early 80s. And they found on sites, the conifer, I think that generally refers to like pine plantation harvest, like commercial timber harvest. And then scrub in this image refers to like brush management on rangelands and stuff. And they're saying when you do thinning or reduction in woody cover, you get increases in water yield. And the magnitude of that increased water yield with reduced woody plant cover goes up significantly with increases in mean annual precipitation. Note that we have no points on this plot under about 400 or 500 or so mean annual precip. So that's like semi-arid systems. We don't have data at this point. And there have been a million of these kind of studies breaking out different mechanisms, right? What explains these differences? This one's taken from Zhang 2001. The solid regression line on the top is the relationship between annual evapotranspiration, right? Combined evaporation and transpiration, water lost from leaves, in relationship to annual rainfall. The top line is the regression for forests. So we have higher annual evapotranspiration compared to this dashed line for grass-dominated systems, lower annual evapotranspiration. So, the lines are way more spread out when you get to tropical systems, super humid systems with rainfall above, 1,500 and 2,000. We're kind of closer to 1,000, a little under 1,000 mean. though we have very high variance, as everyone knows, in our annual precipitation. So these are kind of core findings. There have been a lot of studies refining, interrogating our understanding. So note also that the lines are totally together. They don't diverge at all under about 500 millimeters per year. So semi-arid and arid systems, you don't really see this effect. So one mechanism to explain that is just that whatever plants are on the landscape are capable of transpiring all plant available water in these super arid systems. So it doesn't matter if they're cactus or shrubs or trees or grasses, they just can use all the water that's available to plants. Basically all the water that has essentially any residence time in the rooting zone or in the rooting substrate. We'll keep moving. Here's another recent one. This is from last year, a global synthesis on the effects of thinning on hydrological processes, implications for forest management. So, I pulled out a couple of points here that I thought were salient. The results showed a significant increase in net precipitation, soil moisture, and tree level water use after thinning, while decreases in transpiration. So let's talk about that a little more. Increases in net precipitation, that kind of refers to what is sometimes called through fall. So net precipitation is just the precipitation that actually reaches the land surface and isn't intercepted by tree canopies. So that's pretty easy to accept, right? Increase in water that reaches the land surface is caused because we have fewer trees intercepting, tree canopies intercepting rainfall. And so that same effect shows up in increased soil moisture. We also have increased tree level water use, right? So this is like a feedback whereby if we remove some of the trees from the system, in this case, they're talking about thinning on the WQPL. We more often use prescribed fire to that end. Tree level water use. So we're talking about the trees that are remaining after you do some thinning or prescribed burn in our case. The remaining trees can use more water, right? So if you have a denser stand with more trees in it, there's more competition for water and more limitation for water. So if you remove some of them, that means there should be more moisture in the plant, which has the consequence of that it's less flammable. And then decreases in transpiration after you do thinning, that means stand level transpiration, right? The whole stand, if you remove a bunch of the trees, even though the remaining ones, individual trees, are using more water than they otherwise would have, at the level of the stand, there's less transpiration. That's that same signal we saw in Bosch and Hewlett and Zhang 2001. Thinning intensity of about 50% of the stand density is determined as a threshold at or over which hydrological processes are significantly affected. So early estimates of that were saying maybe you need to remove 80% of the woody plants before you start seeing significant hydrologic benefit. A few decades later, we see, no, 50 is generally adequate. That's when you start to see a statistically significant hydrologic response. So if we have a woody encroached grassland at, say, 100% woody cover, and we move it down to 50, that's when we start to see that significant effect. The duration of thinning effect can be set between a low of 2.6 years for through fall and a high of 8.6 years for soil moisture and transpiration. So that means these effects, these hydrologic responses to changes in woody cover, are relatively short-lived. It's not like you can go in once and do a prescribed burn or something and then say, oh, we fixed our water problems. That's not how it works. And so a mechanism to explain this is that there's a time lag, right? So if we reduce the amount of transpirational biomass in the system, it's going to recover. It's going to recover pretty quick. And then it'll sort of be able to get to that pre-treatment equilibrium where it's transpiring just as much water, for example. So those were kind of global meta-analyses. These are both from the Edwards Plateau. So Dugas et al. 1998. This is from the Seco Creek watershed. So Central Hill Country, a little drier than us. I mean, Central Edwards Plateau, I should say. The way they did this, they set up monitoring towers on 2 adjacent catchments. In 1991, they spent a year just monitoring ET as a percentage of precipitation. And they found these are pretty comparable watersheds. Their hydrologic properties are similar enough so as to constitute a good basis for comparison. Then they did a thinning treatment. This isn't clear cutting where they're removing every single woody plant. They're just removing immature trees and shrubs, recent encroachment, as they describe in this study. Then they continue to measure ET, and they see higher ET for 1, 2, 3 years post-treatment in the untreated site. So they've effectively reduced evapotranspiration from woody plant removal. But in the 4th year, not only is the effect gone, it's offset a little bit. So the treated site is, transpiring more water in that 4th year. So this is consistent with that mechanism that, you remove transpirational biomass, you make more water available for, in our case, groundwater recharge, but it's a short-lived effect. At some point, the transpirational biomass recovers, not just from recovering trees, but of course, grasses also transpire a lot of water, especially in the growing season. And a mechanism to explain why is it a little higher? We don't really know, perhaps, as they suggest in the article. It's because there's more stored water on the site. So they've got a little more water available from those few years where there was a lack of enough transpirational biomass. And so they kind of overshoot the untreated site. Same sort of study design here on Banta and Slattery from 2010. This is in Bexar County again, Honey Creek, so near San Antonio. This is a huge issue for San Antonio. Their sole water supply source is the Edwards Aquifer. It's an important one in other parts of Central Texas too, of course. But in the top line, actually, let's go the left side. You have the reference watershed, and then the right side is the treatment watershed. Again, they've instrumented it with towers that measure evapotranspiration. The equipment they use is kind of the gold standard for this kind of research. And then they've also put in like flumes that measure runoff in the creeks. So they're measuring precipitation. They're directly measuring evapotranspiration and runoff, and then they infer recharge as kind of the difference, So this is kind of the best instrumented and longest term study of this kind from the Edwards Plateau. The reference watershed, so they have, this is a 10-year study. So I think it's like a few years, 2 or 3 years, they just monitor these two watersheds, and it's the pre-treatment plots on the top line is what we're seeing. And so they're pretty comparable, right? The basic hydrologic function here, these pie charts, these figures look really similar. The green is evapotranspiration, by far the biggest part of the water budget. The purple is recharge, and that's kind of what we're interested in for aquifer protection. And then, the bottom line, the bottom 2 pie charts is post-treatment. So they measure for a few years, then they cut all the immature, the small juniper trees and shrubs. So there's still significant woody cover in these systems, but they are able to measure a pretty marked hydrologic response. So the bottom line is post-treatment in the reference watershed. The numbers are pretty similar, which makes sense because they didn't do treatment here. And then in the treatment watershed, post-treatment, we see a 4% reduction in evapotranspiration. Not that much, right? Pretty modest reduction in evapotranspiration. We see a 7% increase in recharge. So 7% of the total water budget doesn't sound like much. However, as a proportion of overall recharge from 17% to 24%, that's a 40% increase in the actual water supplied to the aquifer. So over a 10-year period, this seems to be a significant impact. Now, there are a ton of ecohydro studies from the Edwards Plateau. It's a really well-studied region. I've pointed out these 2 so far because they do the best job of kind of closing the water budget and comparing treated and untreated and looking at recharge, inferring recharge by measuring evapotranspiration and precipitation. So you might so far think, wait, you're cherry picking these certain kind of studies. We'll talk about other studies coming up here that give a different signal. So don't worry. And I'm just explaining why I've chosen these 2. That water budget is a pretty hard thing to measure. We've only done it a couple times in the Edwards Plateau, but it is in fact consistent with the global research, which we reviewed in those meta-analyses earlier in the talk. So a couple of more examples of research from the Edwards Plateau. This is Hwang and Wilcox, 2006. Wilcox, again, one of the co-authors of our land management plan, very prolific author on this topic. And they're using runoff as the thing that they are measuring as a proxy for overall water yield. The logic being the basins that they study, actually the basin that they studied has spring flow. So, they're measuring stream flow, and that stream is fed by a spring. So it includes runoff and this kind of proxy for recharge because it's measuring changes in spring flow. The lines for overall, the regression line for pre-treatment and post-treatment, they're separate, but they're not significantly different, statistically significant. Summer, they're very similar, definitely not statistically significant. Non-summer difference between pre-treatment and post-treatment, they are significantly different. So this post-treatment has higher runoff than the pre-treatment. And so this points to a mechanism of that our C4 grasses are really only metabolically active during the growing season. Whereas, which is like sort of like the hottest part of the year, really kind of May through September for the most part. Whereas the native woody plants that dominate in this system that are evergreen have a much longer growing season. So far we've talked about changes in transpirational biomass can explain this change in ecohydrologic function in response to disturbance. And now we're also saying changes in the growing season length can be an important mechanism to describe this phenomenon. And then here we have Jackson et al. 1999. They're measuring rooting depth in caves. So they go into caves, they harvest fragments of root material, and they use like DNA analysis to identify the species. So other work by this same research group found the global maximum for rooting depth of herbaceous species is less than 5 meters. So we think, there's that popular image of rooting depth of prairie plants. It can be a little misleading. Woody plants are rooted way, way, way deeper. Also, like those really deep, those deepest roots of herbaceous plants don't tend to use much water. It's a little confusing. There's a blog called The Prairie Ecologist that's very popular, and he's got a cool post about that. Anyway, by contrast, woody plants, here we have Q fusiformis, that's plateau live oak, 22-meter rooting depth, 18-meter rooting depth, 14, 11, super deep roots for live oak comparatively. When you get to 9 meters, you start to see cedar elm roots, and then 8 and below, it's cedar elm and ash juniper mostly. But so all of the above, all of these woody plants are deeper rooted than herbaceous. So there's a few mechanisms we're talking about that can explain this difference in evapotranspiration in the Edwards Plateau. Rooting depth, growing season length, and the amount of transpirational biomass. All right, so here's a great study, Wilcox and Hwang, 2010. This was kind of probably the most influential, maybe the best ecohydro study from the Edwards Plateau. What he's saying here, it's really challenging to the prevailing narrative of how these processes work. And this came out in 2010. So the red line here is showing the 10-year moving average for precipitation, saying over this 100-year period that we have data for on precip, it's basically flat if we use that 10-year moving average. And then they're showing stream flow is the black line for these major basins in the Edwards Plateau. And the red line is base flow, so that's thought to be supplied by groundwater. And they're showing it recovering, major increase in base flow and stream flow, total stream flow in these basins of the Edwards Plateau in the second half of the 20th century. And their point here is, wait a minute. We all thought that woody plant encroachment decreases water yield, decreases groundwater recharge, but look at the rivers. They all increased in the second half of the 20th century. And meanwhile, it's widely accepted and believed that woody plants encroached markedly in the second half of the 20th century. So what's going on here? And the explanation they offer is woody plants improved infiltrability. And so we had these hammered rangelands from overstocking, the cattle industry, et cetera. And woody, that suppressing grass cover reduced fire spread and competitively favored woody plant encroachment. That actually improved infiltration. So, this focused a lot of attention on ecohydrology in the Edwards Plateau. It really elucidated the concept that just because we have this global prevalent signal of the inverse relationship between woody cover and water yield, it's not necessarily the most powerful driver, the most influential factor that affects the hydrologic function on the landscape. I didn't really 100% buy their interpretation of this for a couple of reasons, but nevertheless, it is a super valuable study. It focused a lot of research on our area and on these issues. So for example, by 1900, William Bray described woody plants encroachment is already really prevalent all over the Edwards Plateau. That was 1904. By 1917, another kind of professional forester named Foster described woody plant cover is already being over 50% by 1917. So those kind of data points suggest this process that they claim happened in the second half of the 20th century may have already been well underway 50 years prior. Also, my colleague Matt McCaw has pointed out the only sites that we have formal analyses of canopy cover in the Edwards Plateau from the beginning, the first aerial images came from the 1940s. Woody plant cover is flat over that period. So Kusenberry Draw, I think some A&M researchers did that one and found woody cover was flat from the earliest aerials. LCRA did this kind of analysis on the Pedernales River watershed. It's at 60% then, and it was at 60% at the time the study came out in 2000s over that 60-year period. Same story from the Balcones Canyonland National Wildlife Refuge. We also have, they do in this study have really good data on animal units, right? The amount of livestock. So just that really intense decrease in livestock grazing in the second half of the 20th century may be implicated, which they acknowledge in the paper, of course, with this great data set. I kind of also wonder if the 10-year smoothing average obscures the impact of the drought in the middle of the 1950s. So as many of you may have noticed, we just finished our most severe summer drought on record. 2011 was our most severe annual drought on record. But this drought in the middle of the 1950s dwarfs those. That's the most intense multi-year drought on record. And so, looking at these plots, I kind of think, well, is it possible that this 15-year period after that drought was a lag time during which hydrologic function took to recover? So it's not really a phenomena of the second half of the 20th century. It's more just post-drought. I don't know. Anyway, those are just some outstanding questions. And this was really powerful research to get people to question what was long held as an assumption of like, this is the most this inverse relationship between woody cover and water yield is the most prevalent and dominant story in ecohydrology. Moving on. So more recent work from the Wilcox lab. And again, our land management plan, our current one for the water quality protection land, it's a 10-year sort of thing, was completed in November of 2022. So in that same year, the Wilcox lab produced this paper proposing the idea of ecohydrological connectivity as a unifying framework. So where we see disparate, apparently contrasting hydrologic responses to woody plant encroachment, it can be explained by this framework of changes in ecohydrological connectivity. So in subhumid climates, which are defined as having an aridity index of 0.5, that means your evaporative demand is twice as much as your average annual rainfall. Higher evapotranspiration decreases stream flow and groundwater recharge with increases in woody plant cover. And so, that's our kind of climate as a co-author to our land management plan. This is the phenomena that he is diagnosing on our landscape. And so we should do grassland restoration to benefit groundwater recharge to counter that process of woody plant encroachment, that hydrologic consequence of woody plant encroachment. if you go drier to semi-arid, so up on the Edwards Plateau, that's an example of that. We see enhanced infiltrability and lower surface connectivity, and that decreases surface runoff, right? So in non-karst areas, that is, say you have areas that don't, where your water supply is not from an aquifer. Most places the water supply comes from impoundments on rivers. So if you decrease surface runoff because of increased infiltration associated with woody plant encroachment, you get way lower water yield in those impoundments on those rivers. In karst, he's saying these are the kind of systems we have reduced residence time of water in the rooting zone. We have shallower soils. We have rapid recharge. So again, this kind of gets to the kind of system where whatever plants are there are going to be able to take up all plant available water anyway. So if you have enhanced infiltrability in these kind of systems, you can actually see enhanced groundwater recharge, with the caveat that they have to be semi-arid or drier. So here I just want to quickly, we're going to just talk about some more of these kind of quirks of karst systems and how the ecohydrology may work a little bit differently in karst compared to other substrates, for example, deep sand. So, this is a generic diagram of karst. So karst terrain is defined by having caves, aquifers, and springs. Almost everywhere that we have karst, it's limestone dominated. So limestone, dissolves in water and it forms caves, aquifers, and those discharge at springs. A few places have other substrates like dolostones. And the important concepts in this image are we have these dark blue arrows show diffuse recharge. That's where water kind of more gradually has to percolate through the epikarst. The epikarst is the area between the soil surface and the top of the aquifer. It includes competent bedrock, weathered bedrock, caves, fractures, and other voids, and then the soil surface. And then you also have discrete recharge. In this image, they're calling it concentrated recharge, but in the related literature, it's usually called discrete recharge. And that's really rapid flow. So when you have surface runoff that goes straight to a cave, straight into the aquifer, discharges straight into a spring, that happens so fast that the relatively gradual processes of evapotranspiration don't really have time to work on that water, right? So, changes in ecology, changes in woody plant cover and in ecosystem cover are only going to be able to affect ecohydrology on this sort of diffuse recharge where there's water stored in the epikarst. So this is really cool recent literature. This is collaboration between my mentor at UT, Daniela Rempe, and some of her grad student researchers, and the Wilcox Lab at A&M, and some of his grad student researchers. So it's pretty well known for a pretty long time that woody plants increase soil infiltrability at the land surface. The thing that's really striking about this research is that juniper roots enhance bedrock weathering. That idea has been in the literature for a while, but they've really elucidated it in great detail. This is an excellent study design here. And it's both mechanical weathering, whereby roots exploit existing fractures in bedrock, and chemical weathering. So plants exude chemicals from their roots, for example, organic acids that then improve the uptake of nutrients and stuff. And so we have softer bedrock, we have more permeable bedrock, we have this kind of fractured, deeper layers of this fractured bedrock under places with woody plant encroachment compared to places that are in grassland for a longer term. So if you look at the standard text on this kind of stuff, Schlesinger's biogeochemistry, they will say woody plant weathering of bedrock occurs on geologic timescales, 10,000 to millions of years, tens of thousands to millions of years. There is a study on karst terrain showing that it happens over centuries. This one shows it over decades. So orders of magnitude faster than earlier estimates. And so in this paper, they cite two possible ecohydrological consequences of this. If you have plant roots going deeper into the bedrock, softening it and breaking it up, you have longer residence time of water in the rooting zone, and you have a greater volume of rooting zone available for plants to plant roots to forage water. The combined result of both of those processes could mean more evapotranspiration, right? So if we think of a karst system as one where you have a lot of rapid runoff, that's what drives aquifer recharge. This increased bedrock weathering could slow those processes down, making more of the water budget available for evapotranspiration. You also have the possibility of increased or enhanced weathering of bedrock. That means fractures and softer and more permeable rock layers can intersect more existing flow pathways, right? So it could accelerate and increase groundwater recharge. Both of these processes should be happening.
So we know from other research that, you know, deeper soils would predict greater sensitivity to changes in woody plant cover. That is greater hydrologic sensitivity. So if you have really deep soil, then that deeper rooting depth of woody plants goes a much longer way in increasing transpiration compared to if you have shallower soils. So we should expect in karst systems a lesser magnitude of sensitivity to changes in woody plant cover. And so this increased bedrock weathering sort of process could increase rooting depth, but this is like in the tens of centimeters scale. To actually get at this hydrological niche partitioning between woody plants and herbaceous plants, you would need to get differences between, you know, 2 or 3 meters of soil depth for rooting depth for herbaceous plants compared to, you know, 10-ish, or say 8 to 10 meters for juniper as a maximum rooting depth, and then 20 and even higher for plateau live oak. So I also want to point out that, you know, in ecohydrological research, in karst systems, the pattern of rainfall is really important. So if you see, you know, very intense rainfall where a negligible proportion of the precipitation event is stored in the epikarst, and a vast majority of it goes to discrete recharge features, which we'll define in the next slide a little more precisely, then changes in woody plant cover are negligible in terms of their impact on hydrologic response. On the other hand, if you have a precipitation regime where most of the water is stored in the epikarst and in the rooting zone before it becomes available to recharge, or instead of going to discrete recharge, then changes in woody plant cover can be much greater. And so the consequence of that is that you could have studies that basically precisely when your monitoring regime begins and ends can determine whether or not you get a neutral or inverse relationship between woody plant cover and water yield. So I think that's another kind of source of the controversy here. I kind of, the stuff that I've presented so far, I'm sort of emphasizing that these studies where they instrument the watershed to include direct measurements of evapotranspiration, or I guess indirect, but just some measurement of evapotranspiration, and they also include a long time scale, like multiple years. So that would reduce your sensitivity to like just this rain event, precipitation event, versus like the net effect over time. So those are the kind of studies that I think are best at getting us this question of calibrating how does the Edwards Plateau function compared to these global meta-analyses. But studies that measure like discrete events, shorter timescales, discrete flow pathways and recharge are much less clear and harder to sort of contextualize with these global meta-analyses.
So next we'll talk about this biotic pump idea. So we have one consequence of enhanced evapotranspiration with woody plant encroachment or increased woody plant cover is that less of water is available for groundwater recharge. Another consequence of that, of higher evapotranspiration, there's this cooling effect. Evaporation, the conversion of liquid water to water vapor, consumes energy. And so that cooling effect creates low pressure and draws in atmospheric moisture. So at continental and global scales, if you have increased woody plant cover continuous from maritime climates further inland to continental climates, you should see enhanced atmospheric moisture circulation further inland. A lot of people, this kind of idea was first proposed in the formal literature in about 2012, I think. And many were and continue to be sort of dismissive because there have been sort of crackpot ideas about plants making it rain or something. But the theory was good. The physics were good. The math was good. And this idea has been proven out over time. So I could only find like one good like empirical study of this at a large scale that was compiling observations from around the world. And it looked like the only places that it was observable in like the 10 years since people have been looking for this effect were in the Amazon, first of all, where, the most intense hydrologic cycling in the world was decreased from deforestation and clearing. And so then there's a lot less evapotranspiration, a lot less atmospheric moisture, and that translates to significantly less precipitation. So changes in woody cover actually affected the weather, and that's been documented. The other place is in the Gobi Desert, where the Great Greening Project, the Chinese government has been doing. They're planting grasses like in the desert on this super large scale. So you go from a really barren landscape to a grassland, and that's a really big proportional change in evapotranspiration. And then that sort of directs the cycling of the circulation of atmospheric moisture a little further north than it would have to kind of follow that cooling effect of transpiration. But most of this work still remains in the theoretical and modeling realm. So this is Chris Su is one of the ecohydro folks at Texas A&M, and they modeled this in 2013 for the Southern Plains. And these 4 images on the left, we have from current conditions to a 10% increase in woody cover in A 40% increase in B, 70% in C, and 100% in D. That means anywhere that's climatically capable of growing a shrub or tree in the entire Southern Plains is growing a tree. And this is the response. You get the purple shows they're pulling a little bit of moisture from surrounding areas and the Gulf, and it's making a really big difference for precip in this kind of Dust Bowl country, northern kind of panhandle area. No real change, right? Because we already have significant atmospheric moisture circulation on the coastal plain, and then this kind of modest difference around the central Texas area, 5 or 10% increase in precipitation. That's from 2013. This other paper on the right, this is a global scale, same kind of thing in the journal Nature. It's like, one of the most reputable scientific journals in the world. And here in the blue shades, they're showing increased precip. And this is the 100% version, right? If everywhere on the planet that's climatically capable of growing a tree or shrub is doing so, then you get extra precipitation in these places in blue. However, they're also overlaying that with increased aridity, because that extra evaporative demand means water lost from the soil, less plant available moisture in the system. And so, the water limited parts of North America, the net effect of this is apparently negative, and we see increased aridity. All of these citations from this whole presentation will be available if you want to look at the YouTube. When we post the talk, we'll post links to all this stuff. So how do we operationalize this? What do we do with it? Well, we do on the water quality protection lands. Our goal is to improve the quality and quantity of water entering the aquifer. And so we do grassland restoration. So here's a photo from one of our old growth grassland plots. This is a permanent study plot some collaborators that work on savanna conservation. This photo was taken in 2019, and the kind of grayed out brush on the edges here shows the response of a summer fire. This was a very hot, dry fire for our purposes. It really is just pruning the open grown woody plants and that first layer of woody plants by the woodland, but not going through the woodland, not having canopy fire or crown fires. And this is like outstanding diversity of the kind of indicator species of high quality rangeland grasslands. This really prominent one is Liatris covered in seed. So we come out, we do twice a week on the water quality protection lands. We do various kind of grassland restoration activities. So please come out and help if you're interested in that kind of thing. So seed harvest is one of the more popular activities. We also do seeding. This is an area that was burned in June behind me, and I'm just waxing on about things like I do. And a lot of the barren spots in between the grasses, that's from the invasive grass King Ranch bluestem that is sensitive to growing season fire. And so we're going in here, we've got some wild harvested seed, high diversity mix that volunteers were collecting directly from the landscape throughout the year, and then some commercial seed as well. We're going in there, improving the diversity and ecosystem function. And with that, we have some 10 minutes or so for questions.
Sweet. Thank you, Devin. Like Devin mentioned, we're going to be posting all of the references so you can check out all the science on the description of our YouTube. We've got a question. So any questions, just pop them in the chat. There's a question related to when you were talking about a slide, I think Douglas et al. 1998. There was a question around what was the treatment. There was a bar chart of a bar graph of treatment versus non-treatment, or treated, not treated. So the question is, what is the treatment? Yeah, that's it. And does reference quote WS mean it doesn't receive treatment?
So the one on the left is that Dugas et al. 1998, and on the right, that's Banta and Slattery 2010. So I think that WS just means watershed. So we have reference watershed, those two on the left, and then treatment watershed are the two on the right. And here we have in Dugas, it's the same kind of study design. They have a much more expensive and refined kind of monitoring tower in Banta and Slattery. But in both cases, they are cutting the juniper shrubs and trees, not the most mature though. So it's not clear cutting, it's just thinning. You leave the big ones. And that's kind of the standard protocol for grassland restoration in the Edwards Plateau.
Great. And then another question, have you monitored water yield or runoff on WQPL lands? And do you see any effect of your restoration activities?
Yeah, so, the first of the infiltration studies was done, that I'm aware of at least, that was done on the water quality protection lands in 2005. They showed way higher water infiltration under trees compared to grasses. And then Nico Howard's dissertation research was extremely refined and detailed water budget of recharge. How much of precipitation goes to recharge? How much is diffuse? How much is discrete? Which of the major watersheds in the Barton Springs, Edwards Aquifer region contribute the most recharge? It's Onion Creek by a lot. All of that stuff, it seems to be one of the best characterized recharge systems in the world in terms of karst. So those are the things that in terms of like water volume and water budget research that we've seen on the WQPL. We haven't done this kind of treated versus control before and after kind of design on the WQPL. I think mainly, we are a land management group. And so I think it would be awesome if a researcher wanted to conduct that kind of research on our sites. There are some challenges for sure. In terms of like finding the perfect site. If you have like adjacent watersheds with the exact same properties and not a lot of interference from the surrounding area in terms of the way these monitoring stations work, that's ideal. But our sites are like right near big highways. and residential areas and stuff like that. So there are some challenges, but if somebody wanted to conduct that kind of research, that would be great. We don't have funding streams for like long-term hydrology research on the WQPL though. So we would need to partner with someone that did. I think the most promising kind of research of that type though, UT has recently acquired a property. I think it's in Blanco County. It's about 20 minutes west of Austin. And that's going to be a permanent eco-hydro monitoring station. Super brilliant folks managing that site in the geology department.
Cool. I have a couple more questions. Are there similar studies to Dugas and the Banta Slatter and Slattery study that we're looking at right now with prescribed burns instead of thinning? And maybe as like an extra to this, if so, like, do you expect to see similar results with this, with burning and thinning?
Yeah, so for sure that's been done, like meta-analyses have been done for the global scale. So there's enough of those studies in the world that you could do meta-analysis and compile them like that. And that certainly has been done with fire. I'll add that to the list of links that we'll post with this video when it gets on YouTube. We don't have any of that kind of research on the Edwards Plateau. It's like when this happened, there's a story here. It was like kind of heartbreaking, but it's like a bit funny too, and like not super surprising. So what happened on Banta and Slattery, this was supposed to be a permanent monitoring station. I think it was funded by the USGS. It's on state-owned, Honey Creek State Natural Area, and awesome design, super smart folks running it. And as happens in the Edwards Plateau, there's a guy on a bobcat cutting trees. And he's maybe not paying like perfect attention to where he ought to be doing that. And he cut the control and they shut down the station forever. So it happened and we were like tearing our hair out, like, come on. But anyway, that site, the treatment site, the long-term plan was to put it on a continuous permanent fire return interval and do a gradual savanna restoration of the project, the way we do on the water quality protection lands with this ET tower in place, always measuring runoff and evapotranspiration and precipitation and inferring groundwater recharge from that. But they shut it down for good.
Oh, okay. Another question, which I think I know how to answer, but there's a question, and let me know if I'm not getting this question right, person in the audience. The question is there a new program underway since the last 10-year program at WQPL ended in 2022? And I'm wondering if this is referring to the land management plan. And if so, I'm going to post a link to that plan in the chat. Is that, unless Devin, this sounds different to you?
Yeah, it sounds right. Yeah, so we update our land management plan once every 10 years, and we got a fresh version approved by council in 2013, finished by our A&M team in 2022. So, yeah.
Great. This is my moment to put a whole bunch of links in the chat, but for now, I'm going to start with this land management plan, which is the one that Devin mentioned in the talk and came up in the question. If anyone has any other questions for Devin, you can pop them in the chat. I know we're reaching the end of our time together here. And again, there's just going to be a lot of more to dig into. I think, yeah, it's really cool to get a little bit of a picture of the complexity of this issue, especially in our region, in our karst region. What kind of do you have any takeaways in terms of your guiding principles for what guides these land management choices for when you think about it on the water quality protection lands? Is there a certain management that you feel like this is the best thing we could be doing for the land and the water?
Yeah, I mean, there's this set of things that we have to consider when we consider land management interventions. And that for example, we want to do right by ecosystem conservation, right? We want to maintain our mature woodland stands, which we have thousands of acres of golden cheek warbler habitat on the WQPL. We want to protect that. We want to make sure they can regenerate and remain good quality habitat for endangered species and woodland species. And we want to make sure our old growth grassland or our remnant grassland sites are well managed too, because those are susceptible to woody plant encroachment. as a degradative kind of trajectory. We also have concerns about mitigating the risk of wildfire, storing as much carbon as we can, given that these other set of concerns, and then water yield. That's our primary mandate, is to improve water yield. So I think, you know, we've talked about a few mechanisms that seem to be key in the water yield issue, right? Rooting depth, transpirational biomass, growing season length. We have that kind of thing where we have like a bunch of mechanisms. Some of them move in the same direction. Some of them move in kind of different directions from each other, and they drive the outcome. Multiple things drive the response variable. Driving variables change, you know, have varying degrees of influence over the response variable, and the relative strength of those influences vary over time. And we have this whole set of things that we want to consider that are important for our land management outcome. So that complexity is what makes this all super interesting, this kind of inexhaustible thing that we can always do better and always understand better and always be more refined and more careful with. Maybe that wasn't really a super on point answer, but that's what motivates me to understand the system better. And that's what makes it such an interesting kind of work.
Right. And we have one question in under the wire, which might be multiple questions, but we'll read it. We'll start doing it. We're reaching the end of our time, but we're going to kind of tackle this question. I think Devin said you could stay over a little bit. So here we go. Do we have an estimate of how much, like what percentage of the Barton Springs zone will need to be protected in natural condition to maintain a level of flow to Barton Springs to sustain endangered species, the salamanders that live there, and prevent eutrophication of the pool? This is the first question.
Yeah, so I don't know that any amount of spatial extent on the landscape can offset these upstream sources that are already in place. So we have, you know, I think a report where the lead author was Barbara Mahler showed prior to, was it 2010 maybe, the water quality in the aquifer increased with rain events, with flow events in Onion Creek in particular. After 2010, it went the other direction. So the upstream sources on Onion Creek at that key threshold of 2010 are the big control that we have on the big source of degradation that we have on the Barton Springs segment. And I don't know that any amount of spatial extent on the recharge zone is ever really going to offset that. Sorry, that's not a super rosy answer.
This gets into the second question, which I'm just going to say to you in case it has you add anything to this, which is, does WQPL restoration and enhancement of lands more than proportionally help offset the losses when the watershed is transformed by urbanization? A simplistic example with made up numbers is 1 unit of WQPL offsets 3 units of suburban acreage, since the WQPL performs better than it did when first purchased due to these restoration activities, thus helping to somehow hold the line.
Man, I think I'll need to think on that. I'm gonna have to get back to you about it. You know, I think at one point I did a kind of a informal calculation estimate, and it was something to the effect of, you know, the extra water yielded from just having 40% woody plant cover on the fee simple part of the WQPL instead of 80 or 100% was equivalent to something like 6 months of low flow. So if we had like an extended drought and aquifer flow at Barton Springs came under threat, this difference that we get from grassland instead of woodland would buy us like a 6-month buffer into that kind of day zero type calculation. In terms of offsetting, I'm not sure like the unit area degradation and quality that we see from suburban acreage, but I bet, yeah, I would like to learn more about that. Outstanding question.